Welcome everyone. Today we have our another new episode and we will discuss on nuclear fission, very interesting innovations and especially emerging economy. There are many student youth community. They love to learn more about topic and we have our world famous speaker Edward, Professor David Smith and Dr. Talib Rafael will join today's session. Professor Edward, what you want to add for today's session?
Well, yeah, about a week ago, there was an announcement of a breakthrough in nuclear fusion. Now, first of all, I'll let your audience know the difference between nuclear fusion and nuclear fission. Most power plants, nuclear power plants, the power is generated with nuclear fission, meaning you split atoms. And that's what went into the first atomic bombs, of course. And it's a very good way to produce power, but a lot of people are concerned, I think unnecessarily so, that the waste products of nuclear fission is radioactive. You got to do something with it. You have to bury it in the ground. You have to deal with all of this atomic waste that's poisonous and toxic. And of course, there's obviously concerns about meltdowns like you had in Fukushima. Chernobyl was different because it was Soviet technology, which is pretty much junk anyway. But it's a concern of people. Nuclear fission is taking atoms and pushing them together and fusing them, which is what happens inside of the sun. And the good thing about that, from the perspective of waste, is that the leftover from nuclear fusion is hydrogen, non-toxic. It's something that can actually be used for industrial and other purposes. So nuclear and the energy produced by nuclear fusion is significant. So this breakthrough that occurred about a week ago is very important, but I consider this to be, in a sense, a proof of concept. The challenge with nuclear fusion has always been you need to put so much energy into producing temperatures many times hotter than the sun that the energy you get out from fusion doesn't equal the energy that you put in. In other words, the more you're basically wasting energy. You're not producing any net energy. What happened about a week or so ago was they were able to produce net energy with meaning that the energy that they put in was less than the energy that actually came out. Now, here's a couple of things. The energy that came out was about enough to maybe heat a couple of teapots so that we can make tea. And that's nice, but not enough to light up a city. And so the challenges in the future are going to be first technological. In other words, to create the technology so this will scale, so we can actually produce enough energy, not just to heat a few teapots, but to actually run a city or to light up a city or to run industries and things like that. But the second thing is this. This is a promising technology, and this is an important breakthrough for those of us who are looking in the future. And the reason, by the way, it's an important breakthrough is that in the future, as a lot of the emerging economies, places like Bangladesh, places like Indonesia, places like the Philippines and the like in the Asia Pacific area, are going to need a lot more energy if the citizens in those countries are to have their living standards coming up to the level of the living standards in Western and the northern countries, and Japan, South Korea, places like that. They're going to need a lot more energy. So looking for new energy sources is a very important thing. But here's the other thing. This is a challenge and something it's kind of a warning, you might say. What we've seen with renewable energy so far, mainly focusing on wind and solar, is it's very, very costly and it's not terribly efficient. And we see what happened in Germany, for example, where they rushed the technology. They decided they're going to get rid of their nuclear fission and they're going to get rid of their fossil fuels. And basically, they became reliant on Russian energy. And you simply can't run an economy that way. Sorry, it can't happen. And what you've seen in Germany, obviously, is that that they've actually had to take down. They actually took down a field, I believe, of windmills, of wind turbines to operate a coal plant again because of the inefficiencies of those kind of energies. So one important thing is not to rush this, not to say, well, we're going to go with this very quickly. First of all, you can't do it because we don't have that technology yet. to do it. And the other thing is to keep an eye on the economics of it. To have this incredible breakthrough required putting billions of dollars into research and development and the technology, and it's going to take a lot more to scale this technology. So it's crucial that we don't make the mistakes that we made with so-called renewables, and that is to rush them, to have governments promoting them. Because if you basically can produce $1 worth of energy and it only costs you $10, well, that just is economically foolish. And since this is the World Talent Economic Forum, I want to make that important point about the economics of this. So as I say, this is an important technology. This is an important breakthrough. It's a proof of concept. And I think in the next couple of decades, it possibly can scale. But you have to watch about the economics of it. You have to watch about not pushing it to the point where you start trying to substitute fusion for other things, and it's simply not ready for prime time, as we like to say in this country. But again, it's an interesting breakthrough, and in the future we're going to need a lot more energy, and it's not going to be able to come. It's not going to come from a lot of the so-called renewables today. It's going to come from other things. It's going to come from nuclear fission, nuclear fusion, among other things. Ideally, natural gas, which will could take us through for another couple of decades at least. So it's a promise. Keep an eye out for it, folks. And it's a good technology. So those are my comments, and I'm going to have to jump off in a minute and look, but I'll catch this on the rerun, so to speak. So take care, folks. And since I'm here in the United States, and many of us are here in the United States, stay warm. It's freezing here. You guys are warm. We're freezing. Take care.
Thank you. Thank
you. Thank you. Professor David Smith.
Well, Sharif, this is a good topic. I happen to have been involved with some nuclear fusion back from my early days at the University of Texas at Austin. 2 blocks down the campus from me was a tomac reactor that was trying to generate a field to hold nuclear fusion as a way to begin to put the places together. Now, I hate to tell you how many decades ago that was, because I guess that fusion reactor there, that tomac reactor, was probably about 1979 or 1980. So nuclear fusion and nuclear fusion reaction is something that is one of the holy grails that has been going on for a long time. Edward gave you some great points about it, but to me, when I'm asked to explain it, the easiest way to explain it is the sun's energy is nuclear fusion. And that is how that power is produced there. And so humankind has been for millennia dreaming about how do we take the energy that the sun produces and the process that the sun produces it and use it here on the earth. And that's really part of what's happening. There's also many different types of fusion, which I'll get into in a minute. But in the United States, the effort that kind of led up to the announcement at Lawrence Livermore National Lab was back in 1920. A scientist suggested that hydrogen helium fusion could be the primary source of the energy that the sun produces. And then later on, quantum tunneling was discovered in 1927, which began to set up some of the ways where that you could begin to do this type of fusion, and you begin to go even further. The center at Lawrence Livermore National Labs, where this discovery was announced, is called the National Information Field, was actually formed back in 2029. So it has a place where this is what they have, I'm sorry, 2009. This process that they announced began way back then as they were getting there. and beginning to do the work and leading us to where we are today. Uh, there's a couple of very interesting things as I look through it, though. Uh, nuclear fission, which is what we see in the nuclear reactors that Edward talked about, is 8,000 times more efficient. That is at producing energy than traditional fossil fuels. And that is part of the energy density. I had the privilege to lead an energy density storage roadmap for the United States. And that type of radioactive fission was one of the highest sources of energy density they are. Um, now, if I begin to take that nuclear fission and compare it to nuclear fusion, the estimates are way all over the place, but it's estimated that it's more than 100 million times greater efficiency produce power using nuclear fusion than it is even nuclear fission. And and that's really where we see this going. Now, this breakthrough, as Edward rightly pointed out, is a very small breakthrough right now. The amount of positive energy wouldn't buy us much today. But the process that we have converted over from being energy negative to energy positive is a huge one. I mean, if I look in some of the other places with some of the renewable energy that we're producing today, many of those processes are still energy negative. It takes more to put in, build, operate some of the renewable sources than they actually produce in total output. And that is one of the reasons why this nuclear fusion announcement is so good, is that it's crossing the threshold to be a positive energy source. I mean, even petroleum, even oil and gas and natural gas, it takes energy to produce those. Now, in some of those, we do get energy positive outputs, but it's not a one-for-one type of activity. And again, if I look at this nuclear fusion announcement, it's going to take decades to see it refined, to see it transferred. Lawrence Livermore Lab is not the person who's going to bring this to market. So it's going to go through their technology transfer processes, and you'll probably see companies like GE and others who have built many of the nuclear fission reactors try to be the ones to step up and commercialize this technology. But this is a really promising one, and it depends on the packaging of this. What the other very, very important breakthrough on this particular one is how they did the containment field. Most of the containment fields where you've looked at nuclear fusion have used plasma. It's used things where you had to have the containment around it near absolute zero. High temperature superconductivity materials were having to be used for it, which are very expensive to produce and maintain. This approach was very simple. I mean, it was using lasers and things to create a containment field. And so it's a very different approach from the high plasma reactor containment fields of the past. And that holds promise for it beginning to spread globally very rapidly once it starts its commercialization. The other thing I'd like to say, since we're talking about energy today, is the other thing that will help, particularly in developing nations, is if you look at what some of the advanced countries have done that have launched deep space satellites. They have done a very good job of using a concept called nuclear decay. And nuclear decay is not an active fusion reaction. So it's not with all the risk, like Edward mentioned, Chernobyl and others. It doesn't have that risk, but it's a great way to produce limited amount of power without much use of resources and infrastructure to get there. And I really think that's an opportunity for us to begin to look there. But just to kind of come back and put this whole thing in a framework. You know, we know we can produce power today from water and hydropower. We know we can do coal power. We can do natural gas. We can do oil-based power. But then moving further down there, we know we can do wind power. We can do wave power. But then where we see nuclear fission, which is where most of the nuclear reactors today, this nuclear fusion has a couple of sides. There is the classic nuclear fusion, like what you saw demonstrated at Lawrence Livermore. And again, don't underestimate the importance of that, but it's going to take a while. And there's also a concept called cold fusion and uranium type of fusion that are still in the lab, still being worked on, but it is one where it's going to make it really happen. The other thing is the U.S. is not alone here. Earlier in the year, a lab in UK called the JET Laboratory also made an announcement of not quite fusion, but it was getting there, where they squeezed together two forms of hydrogen. And it's also a building block to getting to a commercial source of fusion. So we're seeing that's coming, a lot of advancement. I hope and I think we'll see this will spread very rapidly, where nuclear fission, because of its ability for misuse, was very restrained in its distribution. This one should not have as many constraints there as it begins to be commercialized, but mass commercialization is probably still 20 years away. Initial commercialization is still probably a decade away. So great announcement, but it's a stepping stone to get there. So Sharif, I think that's my first remarks.
Sharif,
Looks like Sharif is paralyzed.
So
why don't you go ahead, Donald?
Thank you.
Go ahead, Donald.
Thank you.
Dr. Talib, why don't you
Dr. Talib.
Okay.
Dr. Talib.
I prefer that Dr. Donald starts before me, if you don't mind. Do you mind, Dr. Donald?
Dr. Talib.
Okay, I'll go ahead. I just want to say, kind of lay a little bit of groundwork here. And I want to talk about a little bit what fusion is. And I'm going to start with something that everybody's heard of probably, which is hydrogen bombs and atomic bombs. And atomic bombs are really quite simple, and which makes it one of the things that makes them dangerous. Is what happens is very, very large, unstable molecules, specifically hydrogen-235 and plutonium are the most widely used molecules. They just naturally break down. Well, I'm going to back up a little bit. Inside of a molecule, there's a couple of particles, one called protons and one called neutrons. Neutrons have no charge at all, but protons have positive charges. And as you know, unlike things attract, so if they had a positive and a negative charge, like a magnet, if you've ever had a magnet, you notice that you can, two magnets, there's one way that you put them together and they repel each other. And then the other way, they attract each other. They stick together. And so what happens is that inside the molecule, inside the center of the atom, they should repel each other because they all have positive charges, but they don't repel each other. And the reason that they don't repel each other is because there's this force of nature, one of the forces of physics called the strong nuclear force. And that is energy. And that energy holds the nucleus together, this strong nuclear force. And with these very large molecules like plutonium and uranium-235, this force is not strong enough to hold the molecule together all the time. So these molecules break apart and they release energy. And that's what makes them radioactive. When they release the energy, they release sometimes little parts of the molecule. So they'll go flying out at high energy, and that high energy particles will hit you, and the higher energy particles will actually cause damage to you, which is why radioactive things like plutonium will cause damage. You don't want to be around it. Radium, plutonium, uranium-235, various kinds of radioactive material. You don't want to be around it because it'll these particles of energy will come out and they'll hit you, or actual little particles themselves, electrons, alpha particles. They'll hit you and cause damage. And what happens is that if you put enough of that stuff together, they start hitting each other. And the particles that come out hit the nucleus of the other particles, and they start breaking apart. And once they break apart, they send out even more, and they all start sending out so many that the entire pile of them basically all start sending out all their energy at the same time, and that causes a atomic reaction. And so nuclear fission means break apart, is the act of these things breaking apart all at the same time. So fission reactors, what they do is they're very, very careful, and they get it to break apart at exactly the right rate, that it creates enough heat that it doesn't break apart all at the same time, but it breaks apart just enough that it creates the heat so that you can boil water, basically, and use that hot water to run a turbine so that you can use that energy to produce energy. And since all those particles are coming out, you have to be very careful and make sure that that nuclear reactor has lots of protection so that those radioactive molecules don't come out and hurt people. That's why nuclear reactors can be very dangerous, because they have lots of these molecules and lots of these particles coming out. The way nuclear fusion works is that it turns out that hydrogen molecules, it takes less energy to be a hydrogen molecule than it does to be a helium molecule. So the nucleus of a helium molecule has 2 protons, and the nucleus of a hydrogen molecule has 1 proton. And if you hook the 2 protons together, it takes less strong nuclear force than it does to have a single hydrogen molecule by itself. And so when you hook the 2 together, it releases that energy, and that energy is far, far more energy than the energy of breaking the molecule apart. But in order to get them to hook together, you have to use a lot of energy. And so once you can get them to start, it's the same kind of thing. Once you can start getting them hooked together, that energy causes, if you have a lot of hydrogen around, that energy causes the other hydrogen to start hooking together. And that's what happens in the sun. The sun is a whole bunch of hydrogen, and the hydrogen is start hooking itself together. And the energy from the hydrogen hooking itself together causes the other hydrogen to hook itself together. And that makes the sun work. And so the way that hydrogen bombs work is that they have a basically regular atomic bomb, which creates enough energy to start, and hydrogen, and that creates enough energy to cause the hydrogen to hook itself together. And then that creates even more energy. So that causes the huge amount of energy from a hydrogen bomb, which is far more dangerous than a regular atomic bomb. But an atomic bomb, as you know, is a huge amount of energy. So in order for us to create fusion, we're looking at needing a lot of energy. So we've been trying to, we can't set off an atomic bomb in order to make energy so that we can power our lights and power our industry and things like that. We can't do that. So what do we do? How do we get enough energy to start getting the hydrogen to hook itself together so that we can use that energy from the same kind of energy as the sun uses? And that's been our problem. How can we do that? And we've been trying without, doing something where, like setting off an atomic bomb, which isn't going to, that isn't going to work for us. And that's been a struggle in order to get fusion to work. And what we just did, or the scientists just did, is they used a bunch of lasers. And lasers, of course, as you know, can have a lot of energy. And they took all these lasers and they all aimed them at some hydrogen. And that all those lasers together were enough energy that it caused the hydrogen to hook itself together and create helium. That's the result of the hydrogen hooking itself together. And the energy that it took to run the lasers was less than the energy that was created by the hydrogen hooking itself together. And that's what worked. But setting up a bunch of lasers like this in order to do this isn't very easy, and it isn't very stable. And capturing the energy that's created in a circumstance like that also isn't very easy. So right now, what's happened is that we've managed to basically create a test situation where we've managed to do it. But changing from this test situation where we've managed to do it into something commercial is a challenge. And it's exciting that we've created a demo, a test situation that's allowing us to possibly do this. But we don't know yet how we're going to take this test situation and turn it into something that we can commercially use. David's optimistic. 10 years is optimistic. 20 years is probably more reasonable. It's not going to be soon enough to help much with climate change. I want to point out that the organization that Edward works for and has worked for is completely financed by the oil industry. And it is an organization that's purpose is to basically be a cheerleader for the oil industry. And so that's what he does for a living, is promote the oil industry. And we can talk about this, but California now has let's see, I've got this in front of me, but we've got something like a third of our power now is from renewable energy. And it's a false dichotomy to say that we're either all renewable energy or no renewable energy, because the degree that we start using renewable energy and start using less petroleum, we're using less petroleum. And the petroleum is putting greenhouse gases in the air. The temperature is rising. The glaciers are melting. Greenland is melting. Antarctica is melting. Crops are failing all over the world because of the fact that of climate change. Storms are getting worse all over the world. People are having to leave where they live because they can't live there anymore because the climate's changing. There's absolutely no question about it. And technology is existing to be able to start transitioning from fossil fuels. The company I'm working with, we can create a transportation system that not only doesn't use fossil fuels, but it is positive. It creates energy. It doesn't need fossil fuels, and it makes more energy than it uses. So it's incorrect to say that alternative energy. California just leased about $750 million worth of offshore space for wind farms, and somebody paid $750 million for it, so they think it's worthwhile. It's happening, and it's important that we do it. It's got to happen. So the beauty of fusion is it's really exciting that we have fusion. I don't think it's not going to happen soon enough. And I think I explained what it is and why it's not going to happen soon enough. But everything that we can do to try and use less fossil fuels is absolutely critical and important. And that's what I have to say. So thank you very much for the opportunity to share my thoughts.
Thank you. Thank you.
Mm-hmm. Thank you. Professor Talib.
Okay. I'm glad I asked Dr. Donald to speak before me, because what he said confirms what I want to say here. I'm speaking from a developing world perspective here. And the developing world needs even more time than the developed world to apply this technology. You're talking about nuclear fusion. The word nuclear here in our part of the world causes a lot of fear and lots of resentment. And it's a mere word of nuclear. Now, in order for us to be able to move forward, we need to, as Professor Donald said, we need to start depending more on renewable energy, wind and solar energy. And that's something that we need to explore. We're just starting to do that now in our parts of the world. And that is something that is working much better than any other thing. Now, I can see why Professor David and Professor Edward are so enthusiastic about nuclear fusion, but I don't quite understand the logic behind it. I'm not a specialist in all of this. I'm just looking at it from a political perspective. Now, fossil fuels are part of the Middle East economy, the Gulf economy particularly, but they are going to stick to that and try to renew, to extend as much as possible the world dependency on the fuel for fossil fuels. That's going to be the case. Now, how does the developed world will react to that is another story. Now, what I want to say here is let's not all put all our bet on nuclear fusion, because the word nuclear itself is a problem. And it has not good history with us. And I think Professor Donald just explained how critical this is. I think that's what I want to say at this point in time. I will have some more to ask about in the future. Thank you.
Thank you. Professor David Smith.
Well, I agree with actually what Dr. Talib said, is that there is a fear of this, not just in developing nations, Dr. Talib, but in developed as well.
Yes, I
The
know.
word nuclear scares a lot of people.
Yeah.
And most of it is built around the nuclear fission, which is can be very bad, because even the byproducts of it, if everything goes well, have very bad life cycles. They're going to be radioactive for hundreds and hundreds of years. So do not think that that's only a developing nation problem. It's the same here, and I really understand that. That's why, as you look at some of the things where I talked about earlier, one of the places where I see near-term use of material to generate power, particularly in small developing nations, Dr. Lee, is with what's called radioisotope power, which is like what you see on spacecraft, the satellites that are going and leaving our solar system even. It does not have an active reaction in it, but what it's doing is it's using the heat from materials that are decaying to generate power. And that's one thing that can be done in developing nations today if we set our mind about it using those. What I like about nuclear fusion is it generates power in such a way that it would be extremely difficult to take it and use it for bad. Yes, you can use anything for bad, but nuclear fission versus nuclear fission, I versus you, have very different ways to generate power. And nuclear fusion should be very clean as you look at how it can be used. Nuclear fission with the reactors like you see in Europe today, and like the ones in Ukraine, as Donald mentioned, they are inherently unstable. And so you're having to do things to try to stabilize it, to keep it in a critical mass, but not let it go too critical, but yet not let it go too low below critical either. And it's a constant battle to keep it in range. And that's what has made that type of nuclear power so controversial. That and its unintended uses, and the consequences of what can happen when it loses coolant. You know, that's what happened in Japan. That's what happened in the Ukraine before, is that things caused the reactor to go supercritical because it lost coolant and began to melt down. Hopefully with nuclear fusion, as we go and see the totally different approaches, we'll see that being built into it. One of the very interesting things is some of the projects I've actually looked at in nuclear fusion. And again, we are decades away from commercialization out in there. Donald says I'm optimistic, but I'm optimistic in having the ability to begin to look at commercial prototype in about a decade. It will take another decade or two to really distribute that going globally. So Donald and I are more in agreement than he thinks we are as we look out at that. But that again, one of the big things in nuclear fusion, Dr. Tree, is that it's a very clean source of power. It is almost a way to look at power. And I'm going to use this word, and I don't mean it the way it's going to come out. It's almost an endless source of power. If you look at the sun, it's the process that the sun uses. And the sun's been generating power for millennia, going back and look at that. Now, will the sun eventually have an event and become a dark star? It will. So it's not endless. But if we can begin to tap nuclear fusion in a commercially viable sense, And there's a lot of things still left to solve. And security is one of those and others as well. It has the potential to really dramatically change our ability to generate power globally. And one of the other things that I think you'll see here is one of the experiments that was on one of the U.S. spacecraft that just returned to the Earth after being in orbit for actually a couple of years was they were trying to beam power from space down to the Earth wirelessly. And the experiment actually went pretty well. And there's also talk of taking these nuclear fusion reactors, Dr. Tlaib, and putting them in orbit. And because you can create one large enough to generate more power than any one developing nation would use, and using some of this wireless technology to beam the energy down to those countries, which solves many of the infrastructure problems where you would not have to invest as much as building a facility in country, of putting in the heavy infrastructure, not only for the generation side, but for the distribution of that power. So I think we see technologies that can begin to brought to bear to do and address the concerns that you rightfully have. And Dr. Lee, like I said, in a developed nation here too, and being a technologist who has actually worked with some of these companies, I can understand it, but I believe it is a viable source going forward. And luckily for me, I do not have any ties to these where I'm being reimbursed, like Donald had talked about with Edward earlier. But as a pure technologist, I can see it. And as one who has tried to commercialize technology out of NASA, out of the Electric Power Research Institute, and many of the federal labs, including NREL, which is the National Energy Lab that the Department of Energy runs. Lawrence Livermore is the Department of Energy Lab too. All of these are doing work that is not just for the United States. This is work that can be distributed and is designed to be distributed globally. And I hope this is just the first step. But like I mentioned before, another key part of this was just done in UK at the JET lab there. I think some of the work that we saw coming out of University of Tokyo early last year in nuclear fusion, which was talking about a set of software algorithms that can begin to control the fusion process. It's going to take a village to make this happen. And the group intelligence are there because, Dr. Tlaib, you've heard me talk about systems of systems.
Yeah.
Nuclear fusion is a huge system of systems, and particularly how you implement it and implement it in developing countries. It will take a while, but to me, because it is not even though the reaction that you see for nuclear fusion is similar to the reaction in a hydrogen bomb, they're different at the fundamental level. And nuclear fusion with the controls, and particularly since nuclear fusion has to be in a containment vehicle. Like you heard me say, some of the early was in plasma. This one was using a lot of lasers and photons, high-powered photons, to do a containment vehicle for it. If any containment part of it is interrupted, the fusion reaction stops automatically by itself. And so again, there's things, safeguards that can help it, prevent it from being used as weapons. But we need to work on those assurances. This is one of the very few power positive sources out there. Even as we look at generating energy from petroleum and oil and gas and wind and solar, they are all energy negative still. It takes more of infrastructure costs. It takes more in other things to get it going. It takes more in building the facilities that generate it than you actually get out in energy in the long run when you do a plus minus on it. And so the ability to begin to drive to go to energy positive is what excites me about this
Can
as
I
a
ask you a
pure
question?
technologist. But that's my answer, Dr. Cleaver. I hope that helped.
Yes, it helps. It helps. Can I ask you a question, please? Because
Sure.
Professor Donald did mention the outcomes, the possible outcomes that do not have safe results and on this fusion thing. How safe is it?
Oh, I would tell you what I have seen. In the real science on this started back in, well, let me say the 1930s.
Okay.
And there, unlike the nuclear fission side where there have been accidents and quite a few accidents, the nuclear fusion side today has not had accidents. And, and so we'll see that now. Is it, I can be run over by a bus walking across the street, so nothing's 100% safe. But it has a fantastic track record so far. Now, that is mostly happening in the labs, but even with nuclear fission, there were accidents in labs all the time. And we haven't seen that with nuclear fusion yet. Is it 100% safe? No, nothing is. But if I am looking at power sources, a bomb falling on a hydroelectric dam is going to kill thousands of people downstream from it as you have the release of water. And we've seen that happen in places like in China and actually up in Sweden where they lost one of their dams. And I think ended up killing like 5,000 people. You see that with gas power plants, with explosions and things like that. So it's a risk factor there, Dr. Talib, because all of the ways we generate power today have risk. Even windmill power has risk. But for the fact that nuclear fusion is very green and it is going to become a very long-term generator of power from each of the plants, I think it's good to see where it's going to go. But safety, health, containment, the ability to keep it directed has to be one of the design criteria over the next 20, 30 years as it begins its commercialization. It's got at least a decade to go, though, from where you're going to see all these pieces coming together to make it work. And the last point on this, Dr. Tweet, is that it's being used from technology globally. You've heard me say that part of the technology is coming out of Japan. Part of it is coming out of UK. Part of it's coming out of the United States. I know others are working on it. During Expo 2020 in UAE, which was, I guess, really Expo 2021, and you look at some of the work there in the Middle East, in the pavilion there for green energy, there were quite a few Middle East countries who were showing off some of the science that they're developing for nuclear fusion, not nuclear fission, which is a nuclear power plants like we have today, but nuclear fusion, which is where this is going. So I believe as we get that decade plus down the road from now, you're going to see a global effort to make this happen of both developed and developing nations coming together to advance and to begin to commercialize this technology. So I hope that helps with your answer too.
It does. Thank you
Yes.
so much. It's obvious that we are going to come to nuclear fusion, whether we like it or not. But the point is, how safe it is. I'm not sure about that.
Yeah, I agree.
Because in the minds of the people, it has to do with radiation and the massive impact it had on Japan, for example, or on other countries where nuclear incidents have happened, like in Russia and in Ukraine. So how safe that is a very important issue. And I think that needs to be clarified a bit. Again, I say I'm not a specialist in this, but I can see the general outlook about it.
Well,
Yes,
I
please.
want to clarify what I was saying is that with nuclear fusion, remember I was saying there's these very heavy molecules that are breaking apart. And when they break apart, these particles come out with lots of energy and they can hurt you. But with nuclear fusion, what happens is we have to provide a lot of energy in order for these very teeny molecules to hook together, to join together. And if we're not providing that energy, it isn't going to happen. And so
where do we get that energy from?
We get them from lasers. In this case, we're getting them from lasers. And so if the lasers get turned off, the reaction doesn't happen anymore. And when they get hooked together, since these little teeny molecules, hydrogen, it's in the air. There's hydrogen, your hydrogen's around you all the time. It doesn't hurt you. And so all that happens is that the hydrogen's just there. But the big giant molecules, the uranium and plutonium and stuff like that, all by themselves, just sitting there, are releasing these particles all the time. And that's what radioactivity is, the danger. So they're dangerous just being around them. If you just are around them for a while, they'll kill you. And so that's the big problem with nuclear fission. And so when a nuclear power plant runs, it even after it's finished generating energy, it has a whole bunch of this radioactive stuff left over. And so we don't know what to do with it. We don't know where to put it. It's going to be radioactive for 1 million years, some of it. And so but in the case of fusion, there's nothing like that. There's no radioactive stuff left over at all. It's just hydrogen. And so it's pretty amazing that way. And that's the difference.
That's easier. That's much clearer to me now. Thank you, Professor Donald.
And to Lee, the hydrogen reactions that is used in nuclear fusion, the same type of hydrogen is probably going to become the energy source for the future of our cars after electric vehicles. Electric vehicles are clearly a transitional approach to become more clean and green, because electric vehicles are also energy negative big time. And the sustainability is not there because the cost of the battery packs exceed the cost of the car. So that when it comes time to replace like the battery part on a Tesla, it doesn't make economic sense. But hydrogen power, and you've heard about hydrogen fuel cells and other things, but hydrogen used as a material to work in transportation, just like in nuclear fusion, is where the future is with that. But what Donald talked about is the problem with hydrogen is the molecules are tiny, tiny, tiny. And it's hard for us to build containers to maintain those because they will go through the walls of a lot of our materials and escape hydrogen because the molecules are so tiny. And where we can have pipes to ship gasoline, we can have wires to ship electricity and distribute it. Right now, we do not have a good system where I can distribute hydrogen across the country. Even your country it would be a difficult there, even though it's a more compact country. The hydrogen atoms are very tiny and very volatile. They're always moving. But that's what makes them a good energy source. That's what's going to make them a good energy source for cars, for airplanes, and for energy. So I hope that helps too.
Okay.
I do want to say two other things that relate to this that I find very important. One of them is that hydrogen is in water. So what hydrogen's there's a lot of hydrogen on Earth, but it's in water. It's a molecule, and that molecule is hooked to oxygen. And so in order for us to get the hydrogen, we have to separate the hydrogen from the oxygen. And the way we do that is a process called electrolysis. And it's putting a very, very low voltage, one volt is what we use. And it's just basically putting two electrodes in the water. It's fun. You do it as a science experiment in high school. And but it takes a lot of energy to do that. It takes, I just looked it up. It takes, oops, I lost it. But like 35 kilowatt hours to get 1 kilogram of hydrogen. So we need to, but we can make enough with solar to do that. It does take quite a lot of energy to make the hydrogen. But one thing that I want to point out about fusion and comparing it to solar is one of the things that's a problem is centralized energy. And so fusion plants, no matter how well they work, are going to have to be in some place. And then once they're in some place, you're going to have to use wires and so on to get them somewhere else. And as we can see in Ukraine, that's been the biggest problem. The Russians just bomb their energy sources, whatever they are, and they can shut off power. In California, we're very vulnerable to that. We have a central power line that if somebody damaged it, a third of the power in California would go out at the same time. There's just one line that, and that's all over the country. It's like that. And so solar, you can have microgrids, decentralized power. Like my friend here that I'm sort of a business partner is building a subdivision of about 200 houses that has its own solar power and batteries, so that it doesn't have to use the central power system. And you can do that. You can build microgrids. Like you can have like villages that have their own power. They don't need to have power that comes on lines from a long distance. It's not necessary anymore. And so as wonderful as fusion is, I think that it's a solution to some things, but I think that I think for the developing world that sustainable energy is probably a better bet. And that's just my view.
I agree.
Thank you.
I think you're right.
Dr. Talib, what's your concluding remarks for today's session?
Thank you so much. I have listened very carefully to what's being said. Again, I want to emphasize the fact that I'm not a specialist in all of this. So I have more questions to ask, but I won't do that now, of course, because I don't know all the questions that are going to be asked. Now, what is important is to try and convince the people here in this part of the world that that's a better solution. And that's not going to happen with the existence of water, wind, and solar energy that are becoming more and more prominent in this world. And they are producing a lot of clean energy in all sense of things. So my conclusion remark are, we have to be very careful about using this. Now, as Professor David said, this is going to take a few decades to be developed in a commercial way. And it will take another 2 decades to come to the developing world, if that's the case. And then after that, we don't know what will happen. But between now and then, many things may change in the perception of the people. What I'm saying now is that the perception of the people is going to be negative towards this. We can't start promoting it. We cannot promote it, definitely. We can't promote it like we're promoting the water energy. For example, in Jordan here, we have the Red Dead Canal. I'm sure you heard about it. That sea is the lowest part on Earth, 300 meters below sea level. And they want to bring in some water from the sea, the Red Sea, which is at sea level. The Dead Sea is lower than sea level. And the conclusion of that is that when water flows at that very high levels, it would produce energy by rotation, like the wind energy as well. So I think that's a better way of looking at it from our perspective. I don't think now we can promote the nuclear energy, nuclear fusion, we call it. Okay, that's what I want to say. Thank you so much, Shay. That's a very interesting.
Thank
I
you.
learned a
Thank
lot
you.
from this meeting. I learned a lot. I really did.
Thank you, Professor Talib.
Thank you. Thank you.
And
Thank you.
you're always a great inspiration for World Talent Economy Forum.
Thank you.
Professor Donald, what's
Thank
your concluding remarks?
Well, I think that it's been a great session. It's always really great to have Dr. Talib on this because he offers such a wonderful perspective. I think that nuclear fusion is exciting, and I think that it'll. I'm glad to see that it might continue to progress during my lifetime. And I think the things that I said are the most important thing is the climate crisis is on us now.
Yes.
And 20 years is 20 years. So right now, I think it's something that's going to be an interesting thing to watch and an interesting thing to see developed and an interesting thing for the future. Right now, our focus has to be on kind of in a way, two things. One is for the developed world, stop greatly reducing our dependency on petroleum so that we can stop greenhouse gases. And for the developing world, we need to provide them with energy so that they can have
Go
the things that they need. So the children can have lights so that they can read at night,
right.
so that they can study and learn and think, and all the things that they can have air conditioning as it gets hotter and all the kinds of things that they need. But they need to have energy in a clean, sustainable way, and they're not going to get it from fusion and in time.
Not now, at least. Not now.
Yeah, and not in
now.
time. So that's basically what what I'm saying is fusion sounds something wonderful and interesting to watch, but it's not. It's kind of still science fiction. So that's my concluding remark.
Thank you.
Thank you. Professor David Smith, what's your concluding remarks?
Donald, in some ways, I 1,000% agree with you. Like I started saying that 40 years ago, more than 40 years ago now, my office at the University of Texas was down the street from a scientific tomac fusion reactor. And the scientists there, including 2 Nobel Prize winners who were working on that, were 100% confident that that would be in the marketplace within 15 years. Well, 40 years later, it's still not. So, Dr. Talib, it is going to take some time to get there.
Yeah.
But as was stated here, is a lot of the things I do like about this science, and it's science today, it's not technology yet, is that it uses hydrogen. And as Donald said, hydrogen is one of the most plentiful atoms on the earth. And that we'll even see on other terrestrial bodies, like in the moon rocks and things we're seeing with the test on Mars and some of the others, hydrogen is plentiful across the universe. And so to me, it makes sense to look at this as a way to help us address very critical problems across the world. One of the things I think, Donald, where I have a slight disagreement with you is that some of the work I see being done in some of the national labs and other institutions around the world is they're looking at tomac reactors not as massive size reactors the size of power plants or larger, or the size of nuclear power plants. Some of the work being done on these are where they're the size of a van, and it might be a big van when they finally become commercialized. But these are things that could become, and I hate to use this term in conjunction with fusion, but I will. They almost can become point of use power generation. I believe we're going to see more and more point of use power generation happening around the world because of the need for precision power. And Dr. Tlaib, what you're seeing happening all around Jordan and your part of the world is more and more of the need for precision power. And that's why you see countries, particularly in your part of the world, that are beginning to pull more science and technology applications into your manufacturing, into the things. You're seeing some of your, particularly the old hydro power plants, not being as precision power as they should be. And so point of use power generation is going to become very important in the developing and the developed worlds. And Donald is 100% right. Texas needs more precision power. And that's actually, Donald, one of the reasons Texas made the decision to only have limited interconnects to the national grid, was try to keep more precision power in the state. But the point of use power generation is going to become one of the next things happening as you look at energy. And you're the fact that today most wind power has to be out in the country. You're not going to put big wind turbines in major urban areas. You're not going to put wind turbines where there's animals being migrated, because they kill birds everywhere. Solar power and solar panels can be closer to major areas. You can put small point of use ones for microgrids, and microgrids are going to be extremely important as we go forward with this. And point of use power depends on microgrids, not national grids, even though it helps. Is going to be extremely important too. The other place that we're forgetting and we didn't talk here much about is in places, Dr. Tlaib, like Jordan and the Middle East, where you're, in Europe, where you have a lot of trains, you have a lot of big vehicles transmitting materials around the country, is there's technology now that will let me use the motion of the train wheels to generate power as a byproduct. But then we now have battery technology that can be used to store them on specialized cars on the train and then plug those into the grid. Same thing with those large trucks shipping cargo and oil and things around the nation. I can put batteries on those and put generators on the wheels and generate kinetic electricity off of those. So there's a lot of clean ways to generate power, and we're just on the cusp now of taking that science, turning it into technology and use. So the next decade through 50 years, we're going to see hundreds, if not thousands, of new ways to create power coming out. And most of them are not going to be those massive plants, but they're going to be more point of use generation, which is what I'm seeing. And this whole concept of microgrids is going to take the world by storm, because like in Ukraine,
like the solar energy.
Yeah, like the solar energy, because those contribute to microgrids. So the putting solar cells on top of large buildings and factories is creating a microgrid. I can do the same thing with potentially small fusion reactors down the road to do that same thing. So
the other thing is,
that's where I think it's going.
Okay, Dr. Donald. The other thing is, you only invest once in the infrastructure of these setups, and you get after that a pure reward back.
Right.
But I'm not sure about nuclear fusion. Do you have to keep investing in that?
It's nuclear fusion is not commercialized yet.
Yeah.
But the science of nuclear fusion should create an environment to continually generate power. And the important thing of this announcement is, by it becoming power positive, that means it will produce more power than the investment in the infrastructure
Yeah.
to generate the power. And that is, like I said, the important things of this announcement.
It is very important. It's very important.
Yeah, I
I
mean,
agree.
even solar power, the solar cells have a limited life cycle, and the infrastructure required for those is great, even on top of a building.
Yeah.
And it's all part of pulling these pieces together to create a sustainable energy future that's green. And that's the goal. And I believe this can be part of it. But again, what I love about the fusion, and it's science, not technology yet, is that the very premise of it is it's a point of use power generation source, and it's going to work with all these microgrids. And you can take microgrids and connect them together to create larger grids, but the premise of them are microgrids. So if I were to power, let's say, half of a city off of a fusion reactor, and I don't use the word nuclear fusion because it's really hydrogen cell fusion
Yeah, that's right.
off of a fusion reactor. That microcell can be connected to others and distributed, but the basic management of the power is going to be in that microcell. There's many cells and microcells, and then you get to larger regional cells and stuff. But
It's
the
clear to me.
microcell is the concept, and that microcell can use fusion. It can use solar. It can use wind. It can use geothermal.
Yeah.
Geothermal is another great source of power to generate power. It can
Yeah.
use hydro. It can use the whole combination and help us move away from using coal, help us move away from using petroleum
First,
and
petroleum.
hydrocarbons where the byproducts are bad. But we have to understand each of those others have problems. I can tell you here in Texas, we have quite a few windmills. And during migration season here, thousands and thousands and thousands of birds are killed running into the windmills.
Really?
Yeah, I mean, you can look at that one there. It's a source of, particularly if they're in migration patterns.
Yeah.
And you see, so even windmills, which you think are very, very safe and clean, they have problems with stuff like that. That with some of the work I'm doing with NASA, we're looking at aerospace. And small planes have flown into windmills at night because the spinning blades, which are hundreds of feet long, don't have lights on them.
Yeah.
So small
That's
planes
right.
have flown into them, and the people have been killed.
What about the solar? What are the shortcomings of the solar?
Solar takes a lot of space. They have a finite life cycle. They get dirty. So in places where there's high pollution or high particulates, like all of the Sierra area of the desert, you'd expect because there's so much sun there and it's so hot, that solar, that's a natural for solar. But because of all the sand and the sandstorms, that shortens the life of solar.
Yeah.
And other stuff like that. So there's not any one silver bullet.
Okay, that's clear to me. Very clear.
All of these working together can create a solution. And it's going to take them working as a system of systems. Because we've talked about the generation. The other missing element in here, and Sharif, sorry to hit here because I know we're over time, is that we have to have control systems that can do this. Our biggest grand challenge is not the generation, but it's the control of. And if I'm a developing nation university, creating control systems for this is something that the developing world is at the same advantage point as any of the developed nations as well too. And that control system is a grand challenge. And it's one that has to be solved. Some of the work I'm doing in looking at how to electrify airplanes and take petroleum off of airplanes is the control system. I can use different types of batteries, even though there's problems and there's life safety problems using batteries. The control systems and the ability to manage that, particularly using life safety, is one that has a long ways to go too. So
That includes the nuclear fusion.
it
That includes the
includes all
nuclear
of them.
fusion.
Includes
Yeah.
everyone. In any place we're generating power, battery, even hydroelectric dams, the control systems of those are decades and decades old.
Yeah.
And they don't use sensors. They don't use the modern tools we have. So we need to spend money to develop the very next generation control system that can control all of these.
Yeah.
And can take care and take advantage of our sensors, that can take advantage of digital twins and modeling, that can take advantage of our ability to make decisions in the microseconds now, where a decision in an old nuclear reactor or an old hydroelectric dam are manual decisions. So you've seen the pictures, even in the Ukraine, where those walls of knobs and buttons and switches, that's
Yes,
how
I've seen
most
that.
of that world is run today. And we need to take it to the next generation control system.
Yeah, definitely. Thank you so much, Professor Donald.
Thank
It's been
you.
very
Thank
educational.
you.
Thank you. Thank you.
Thank you everyone for joining today's session. This excellent session, especially it's very thought-provoking and many audience they can learn about nuclear fusion and all of the technological advantage we can get from this innovation. Thank you, Professor Donald, Professor David Speed, and Dr. Talib Raphael for your
Thank you.
continuous support for
Thank
World
you.
Talent Economy Forum. Thank you.
Thank you.
Bye-bye.
Thank you,
And take care.
David. Thank you, David. Thank you, Donald, very much.
Thank you.
Thank you.
Just
Thank
send
you.
my
Thank you. Bye.
thanks to Edward as well. Bye. Bye.
Bye.
Bye.
Bye.
See you. Bye. Bye.